Now we can analytically predict how the solution behaves when they are continuous. The question gets into shockwaves. Shockwaves are discontinuities where du dx does not exist. Right? Shockwaves are regions where df dx times partial u partial x, where this does not exist. So that's the first time in studying differential equations when differential equation doesn't exist anymore. All right, we have been studying partial differential equations, but along these shockwaves, as you see, there is no spatial derivative, there is no time derivative. All derivatives you can look at is equal to infinity. So there is no point of studying differential equation anymore. Okay, so this is the primitive form. It's not valid. The conservative form, how about the conservative form? Remember partial u partial t plus partial f partial x equal to 0? How about looking at that? When du dx doesn't exist, maybe f is still continuous? Not really, because as long as the shockwave would move, partial u partial t doesn't exist. So partial u partial t doesn't exist. Right? If you have a stationary shockwave, maybe you are in good luck. But anytime when the shockwave moves even a little bit, then du dt across the shockwave doesn't exist. So conservative form is gone. Both of the differential forms of conservation law is no longer applicable. And the last result we have is the integral form. And it is interesting that the integral form actually does not break down at the face of shockwaves. So integral form is the only form that still holds. Let's review what the integral form is. d dt of integration from L to R of any interval, right, times the u plus, and let's focus on Burger's equation, half of u squared L R is equal to 0. Why does it still hold? Even when the space L and R includes a discontinuity. So let's look at that. So let's say this is u, this is x. I mean, when I'm drawing this diagram, sometimes I'm drawing u as the y-axis, sometimes I'm drawing t as the y-axis. So they are completely two different plots. One is like this plot, the other is like this plot. So be careful what my y-axis is. So u is more like this plot. The y-axis is u. If I have a discontinuity, just like that, okay, just like what I have here, and my L and R actually includes that discontinuity. So this is a discontinuity. Didn't do it very well. Okay. Do I still have a time derivative even when the shockwave moves? Yes. Why? Yes, it is still a derivative of the integral quantity. The integration somehow smoothes this discontinuity out. So, for example, and to illustrate why it still holds, let me give you an example. It's the simplest case we can imagine. So we have a shockwave over here, and on the left of the shockwave we have UL. On the right of the shockwave we have UR, left and right. Okay, And the shockwave would be moving in general. So the shockwave moves at a speed of us. So u of shockwave, velocity of shockwave. And let's take a look at, does the time derivative exist? No? Yes? After infinitesimal time, after dt, what would the solution look like? It's going to move a little bit towards the left, or towards the right. And what is the delta x it moves? The x of shockwave is equal to us times dt, right? Oops. Right? So this is how much it has moved. So how much has the integral changed? The integral has changed. Let's represent the integral as the space below the solution, right? So before the shockwave has moved, this is the integral. Oh, sorry. It should end at r. So this is the integral before the shockwave moved. After the shockwave moved, change the different color. After the shockwave moved, this is the integral. Can you see that? Yes, maybe not very much. Let me color this a little bit more. So what is the delta? What is the change? What is the change? Ooh.
So before the delta t, the space is occupied by the green slash region, and after the delta t, it's occupied by the red region. So what is the delta? The delta is the small region over here. It is above UR and below UL, and across the spatial region where the shockwave moved across. So this is actually, in the special case, is equal to what? What is the area of the rectangle? UL minus UR, right? Times dxs, which is us times dt. And this, of course, has to be divided by dt over here. So we can see that the derivative of the conserved quantity of the total amount of stuff is actually a finite quantity, even when this region contains a shockwave. And this formula is actually generally true if you make the regions to be small enough. If you take the L and R to be in the region that is very, very close to the shockwave. So L is immediately to the left of the shockwave, and R is immediately to the right of the shockwave. So that between L and the shockwave, the solution is almost constant as a UL, which is the solution immediately to the left of the shockwave. And R is so close to the shockwave that between the shockwave and R, the solution is also a constant. It's UR. All right. If you take that control volume, actually, the ddt of the total amount of stuff within the control volume is given as this formula. Why is this useful? It is going to help us figure out the speed of the shockwave, us. Alright? Okay, so the speed of the shockwave, us, can be figured out by taking a tiny control volume around the shockwave. So that the left of the control volume, the left part of the control volume is UL, the right part of the control volume is UR. So this is the first part of this integral form, and the second part of the integral form, let's use, is what? Can somebody figure that out? What is u squared over 2? What is the boundary flux? it is of course UR squared over 2 minus UL squared over 2, right? If we take the control volume to be small enough that just encompasses the shock wave. So we get this UL minus UR times US, that is how much the area has gained, how much the total stuff in the control volume has gained over unit of time, plus UR squared minus UL squared over 2 is equal to 0. Right? So US is equal to UR square minus UL square over 2 divided by actually it's I need to move that to the right hand side, so it becomes UL minus UR, right? Divided by UL minus UR. So if you expand UL square minus UR square into UL plus UR times UL minus UR, this whole thing is equal to the average of UL and UR. The speed of the shock wave, okay, from this formula is equal to the average speed the average of the solution the average of the solution on the left and on the right of the shock wave. So if you look at this, okay, on the left hand side the solution almost always match the solution on the right hand side, but their sign is just flipped. Alright, so the shock wave almost has zero velocity, it goes straight. Can we construct a shock wave that moves, that curves? I'm going to take this as a challenge. So who can come up and draw an initial condition so that the shock wave would initially move towards the right and then curve towards the left? Challenge. Alright, anybody take the challenge? So the speed of the shock wave is average of UL and UR. Okay, let's take a 5 minutes break. And if you can figure out during the break, you should come up and we are going to draw something that have the shock wave initially goes towards one direction and then curves and go back towards the other direction. Let's see how you can use that formula here.